This is Lecture 5, Section 4. Now we take a look at the relationship between the electrochemical gradients and membrane potentials. As we saw last lecture, the distribution of ions across an ion-selective membrane depends on two opposing forces. It depends on the chemical gradient, and it also depends on the electrical gradient. So in some textbooks, the electrical gradient is also called the electromotive force, or the EMF, which is the acronym that is used in the example shown here in the figure. So in this particular example, we have a beaker, once again, with an ion-selective membrane dividing the beaker into two halves. This membrane is permeable to potassium, but it's not permeable to chloride. So only potassium can cross the membrane. And essentially at time 0, we are adding potassium chloride solutions, or salt, at different concentrations on the left and on the right. So at time 0, when potassium chloride is added, the net charge on either side of the membrane, as for every positively charged potassium ion, there's a negatively charged chloride ion. But as soon as the potassium chloride starts to dissolve, the potassium chloride salt dissolves on either side, and there's a 10 times higher concentration on the left-hand side than the right-hand side, then potassium will start to move from the left to the right down its concentration gradient as shown here. So once potassium starts to move down its concentration gradient, there's a positive charge that will move across the membrane, but the reciprocal negative charge is left behind because of this ion-selective nature of the semipermeable membrane that's in the beaker. This will cause a buildup, right, of charge that will quickly begin to repel the movement of potassium ions. Now, if you let the system go to equilibrium, the chemical gradient across the membrane will eventually equal the electrical gradient, i.e. the electromotive force. And they will become equal in force, but in opposite directions. Again, this charge difference, it's important to remember that this charge difference is only in the proximity of the membrane. There's no difference in charge in the bulk fluid away from the membrane. And when the difference in charge caused by potassium comes to an equilibrium, that's called the equilibrium potential, right? So the potential difference across the membrane when the two forces, the chemical gradient force and the electrical gradient force, come to equilibrium, that gives us the equilibrium potential for the specific ion that is moving across the membrane. So the equilibrium potential for potassium is represented by E subscript K. That electromotive force, essentially, right, is acting from right to left as the positive charge on the right is counteracting the movement of potassium from left to right down its chemical gradient. Also, the negative charge on the left-hand side is also counteracting the movement of potassium from left to right. Now, it's important to remember that in living cells, membranes actively establish electrochemical gradient, primarily via the actions of the sodium-potassium ATPase pump, and that passive diffusion of ions is controlled by ion channels which are gated. Okay, let's now take a look at some of the mathematical underpinnings of the membrane potential. First, we're going to look at how you use the Nernst equation to calculate the equilibrium potential of single ions. So, for example, the equilibrium potential of potassium, as we saw in the last slide. The equilibrium potential for a given ion, which here we call X, is essentially proportional to the ratio of the concentration of that given ion across the membrane. The equation itself, the Nernst equation, is shown here. It allows us to calculate the equilibrium potential that would be generated by the distribution of ions present on either side of the membrane. It uses the gas constant, which is the letter R, T, calculated that's the absolute temperature calculated in Kelvin, Z, the valence of the ion that is being considered. So the valence of potassium is +1, the valence of sodium is +1, the valence of calcium is +2, the valence of chloride is -1. It also uses another constant, the Faraday constant, represented by the letter F. And the equation shown here uses the natural log of the ratio of the concentration of the ion being considered outside of the cell divided by the concentration of that ion inside the cell. The equilibrium potential for a given ion is typically calculated at 18 Celsius, or at room temperature. So you can essentially reorganize the Nernst equation into a more simplified form. And that's what was done here in the box below, where here the equilibrium potential for ion X, calculated in volt, is now equal to, if you take into consideration the different constants and you convert the temperature from absolute temperature to Celsius and take the temperature of 18 Celsius, then you end up with a value of 0.058 that you divide by the valence of the ion being considered, and then you multiply by the log base 10 of the ratio of the concentration of the ions outside divided by inside the cell. Typically, the equilibrium potential for a given ion is not shown in volt but in millivolt. So you multiply 0.058 by 1,000, and the final equation that you need to use to calculate the Nernst equation in its simplified form is equal to 58 divided by the valence times the log of the ratio of the concentration outside and inside the cell. Okay. So in this graph, we look at the relationship between the ratio of potassium ions outside divided by inside. So that's the relationship between the concentration outside and inside the cell for potassium, versus the equilibrium potential for potassium calculated in millivolt. So using this equation right here. So as the difference in potassium across the membrane increases, you see that the equilibrium potential for potassium also increases. If the concentration of potassium outside and inside the cell are equal, and the ratio becomes 1, then the equilibrium potential for potassium essentially is 0 millivolt. There is no difference in charge across the membrane, and therefore potassium would not contribute to resting membrane potential if the concentration of potassium was the same on both sides of the membrane. Now we know that's not the case. We know there's much higher concentration of potassium inside the cell than outside the cell. So in living cell, the ratio is less than 1. In fact, it's much closer to 0.01. That is, the concentration of potassium outside the cell is about 1/100th of what it is inside the cell. So that tells us that the equilibrium potential for potassium is closer to a value of minus 116 millivolt. The equilibrium potential essentially is proportional to the logarithm of the ratio of the concentration in the two compartments. And for every 10-fold increase in the concentration gradient across the membrane, we see that the equilibrium potential for potassium increases by minus 58 millivolt. So as if we go from 1 to 0.1, you get a minus 58 millivolt increase. If there's another 10-fold increase in the difference in the concentration of potassium across the membrane, it goes up by another minus 58 millivolt up to minus 116, and so on and so forth. So once again, the Nernst equation allows us to calculate the contribution of individual ions to the resting membrane potential of a cell. Okay, so to give you an opportunity to practice using the Nernst equation to calculate the equilibrium potential of individual ion, I came up with the following exercise. So assuming the following distribution of ions across a cell membrane, whereby sodium has a concentration of 10 millimolar inside and 120 millimolar outside the cell, potassium 140 inside, 2.5 millimolar outside, calcium 0.001 millimolar inside, 2 millimolar outside, chloride 4 millimolar inside, and 120 millimolar outside. I want you to calculate the equilibrium potential for potassium, for sodium, for chloride, and for calcium using the simplified version of the Nernst equation that I introduced in the last slide. Now, remember that the resting membrane potential in neurons is roughly minus 70 millivolt. Once you've calculated the equilibrium potential for those 4 ions, I want you to answer the following question. At equilibrium, how will each one of those ions affect the resting membrane potential? Will each one of these ions depolarize or hyperpolarize the membrane? And maybe you can use the discussion function on course link to discuss your answers with other students, and we can talk about also during the virtual classroom.